All right, next, in this unit, we're going to go ahead and talk about transformations and characteristics of logarithmic functions. And so the first thing you need to write up here is that logarithmic functions are the inverse of exponential functions. They're the inverse of exponential functions. So a little bit of a reminder, multiplication and division are inverses, addition and subtraction are inverses. If we want to think of functions that are inverses, we can remember that x squared and the square root of x are inverse functions. X to the third and the cube root of x are inverse functions. And so 2 to the x and log base 2 of x are inverse functions. They are function operations that would undo each other. So that's something that's important to remember. It also means that if we were to take the information that we learned on our last set of notes and switch the x and the y values, because if you guys recall when we learned about inverses, we learned that the x and the y values trade. That's how we're going to relate these graphs together, is the x and the y values are going to trade. So when we look here, we're going to find that instead of having a horizontal asymptote at y equals 0, a log graph is going to have a vertical asymptote at x equals 0. Instead of looking for the horizontal asymptote on the end of the function, we're going to look for the vertical asymptote in the middle of the function. So here's where the parentheses would be. So instead of looking for the k value to find the horizontal asymptote, we're going to look for the h value to find the vertical asymptote. And then for our points, instead of having 0, 1, we're going to have the point 1, 0 because the x and the y have traded since it's an inverse. And then instead of having the point 1, b, we're going to have the point b, 1. b, comma 1. All right, so if we were graphing the function y equals log base 2 of x, then we would have the vertical asymptote, x equals 0. We would have the point 1, 0, and we would have the point 2, 1, a base of 2, 2, 1. All right, we're still going to take the points, we're going to follow them towards the asymptote. So I start with the point furthest away, and I'm going to follow it towards the asymptote. So I can follow it this way towards the asymptote. And then it grows very quickly away. So it goes like this time. So instead of growing up, it grows to the right. Now it still goes up, but it doesn't go up quickly. It goes up very slowly. A log graph actually grows slower than a linear graph. So we think of linear graphs as growing kind of like the slowest there could be. You have like your linear graphs are straight lines. And then you have your x squared graphs, and those grow faster, and then x to the third grow faster than that, and then we say 2 to the x grow even faster. Well, the slowest growing graph that you can come up with is a log function, actually. So these go up forever, but they just do it very, very, very slowly. All right, so we have that vertical asymptote. Here, it's a vertical asymptote, so it does not get crossed. You just have that line getting closer to it. As far as our transformations, we're going to be used to these. So we're going to say that when a is negative, that's a reflection over x. When the absolute value of a is greater than 1, that's our vertical stretch. Absolute value of a is less than 1, that's our vertical compression. The h, if it's plus, that's to the left. If it's minus, that's to the right. So just like normal, it's the opposite of what we would think. With the k, if it's plus, that's up. If it's minus, that's down. And then the b is going to be the base of the log. The base of the log. All right, so we're going to leave this one to do in class tomorrow, so don't write anything for that yet. ln is how people typically say this, ln of x, and they call that the natural log. So ln of x, the natural log, we'll talk about that more tomorrow. So like I said before, logarithmic functions, they have a vertical asymptote at x equals h. Don't have a vertex or locator point. So if we look at this equation right here, negative log base 2 of x plus 1 with a plus 1 on the end. For vertical asymptote, we're going to do the opposite sign of this part right here, just like we normally would if we were finding the vertex or the locator point. So we're going to say the vertical asymptote is x equals negative 1. And then for our transformations, we've got reflect over x, left 1, up 1. And if we wanted to know what the parent function was for this example problem, we would say the parent function was log base 2 of x, and that would be the log graph with no transformations applied. All right, so let's go ahead and move on to the next page, finding domain and the range for a specific example problem. So this graph I thought was interesting when I pulled up the example. This is not uncommon for a problem to do this, especially on your graphing calculators. These graphs, when they approach those vertical asymptotes, they all but become perfectly straight lines, and your calculator goes, oop, that's not a function, it's not passing the vertical line test, and your calculator basically stops graphing it at that point. It doesn't mean that the arrow was supposed to not be there. The arrow was. This is just a limitation of technology. It's because the line is kind of thick. The calculator was having a hard time. The online calculator that I used to generate the graphs was having a hard time graphing how straight this was. And it was getting really close to that vertical asymptote right here at +3. I was having a really hard time graphing that. So go ahead and put an arrow there that should have been there. And it is not uncommon for your graph to do something like that on your calculator or even in a drawing like this. And you just have to be smarter than the calculator and know it should have kept going. So our vertical asymptote here is x equals 3. Just like in our rational functions, we know that the horizontal asymptotes do impact the range. You probably noticed that a lot as you were finding the range on your practice assignments for exponential functions. So today when we do the vertical asymptote, that's going to impact the domain. So when we look at the domain, we have that vertical asymptote. I'm going to go ahead and draw that in because it's going to help me think through my domain for this problem. So the graph this time does not go to the left of that domain. So we're going to say 3 is as far as this graph goes to the left, and then it goes forever to the right. And then for this one, for the range, it goes down forever and it goes up forever. So what you'll notice is that the answers that we had last time, let me grab my notes. Those answers that we had for domain and range last time, they've kind of flip-flopped. So for our exponential functions, when we had domain and range, we used to have domain was negative infinity to infinity for every single problem, and then our range was the problem with the limitation because of the horizontal asymptote. For our logarithmic functions, that has changed. The range is going to be the problem that has the negative infinity to positive infinity every single time for every single graph, no matter what. And then the domain is going to be the one with the limitations because of that vertical asymptote. So it's the exact opposite as what we just practiced. All right. Increasing and decreasing intervals. So again, that vertical asymptote is going to be important because the increasing and decreasing intervals are based off of the x values. This is the one type of problem that is not opposite from yesterday because increasing and decreasing intervals are always just based on x values. So we're not switching. Yesterday they were based on x values. Today they're still based on x values. So here we have our vertical asymptote is x equals 0 right there. So if I put a little stick figure guy right here, It is an arrow, the arrow's going up, but the arrow is being blocked by the asymptote from going left forever. It cannot go left forever. So this asymptote is actually stopping at 0. It tried to go left forever, but it couldn't. It's kind of like there's a fence there. And then over here, this asymptote does go to the right forever, though. And then the stick figure is kind of going down like a big slide. He's like, whee, down the slide. He's decreasing. So increasing interval is none, decreasing intervals from 0 to infinity. So you'll notice that that is different from what we did yesterday. Increasing intervals, increasing and decreasing, you'll notice they never had limitations. They always kind of matched to the domain. This time, that vertical asymptote is keeping our increasing or decreasing interval from being all real numbers. All right, for the maximum and minimum, again, for exponential and logarithmic, we are not going to have a mountaintop or valley for these types of pictures, and so we're not ever going to have a maximum or minimum. X and Y intercept, we're going to skip in the video. We're going to go ahead and find that answer together in class, so we can move to the next page of the notes. Continuity, these graphs are continuous. I wrote exponential functions, but logarithmic functions as well. You can go ahead and cross that out and say logarithmic functions are always continuous. Right? And then here, when we talk about our end behavior, as we look forever to the left, as we look forever to the right, so this one, I'm trying to think, we've done one like this before. I'm drawing a blank as to what it was, but I feel like we've done one like this before. As we look forever to the left, we can see that the left arrow is getting blocked by the asymptote. So I'm going to write that. Left arrow is blocked by the vertical asymptote. And this is going to be true for all of these. We're going to say that the left arrow is going to be undefined. It doesn't go up, it doesn't go down, it doesn't flatten out. It's just undefined. It gets blocked. If you want to think of that vertical asymptote as a fence, you can always draw it in and think of it as a fence that is blocking that left arrow. The graph cannot go forever to the left because it's being blocked. And then as the arrow goes right forever, it's very, very slow, but this one does happen to go up forever, so that one would be a positive infinity. And then just like yesterday, I'll go ahead and leave these last two graphs for us to graph together in class. So don't do any more work on these notes.